Hello again, dear students. I hope you're all doing well. Today we are starting with section 2 of chapter 3. That's about concavity and inflection points or points of inflection. Doesn't make a difference, however you're saying it. Okay, last lecture we talked about increasing, decreasing functions. We talked about critical numbers and how to what was the procedure for finding those critical numbers and intervals of increase and decrease. I'll make a quick review as I usually do that. So last lecture we studied increasing and decreasing intervals. Okay, increasing and decreasing intervals. We studied critical numbers, and we also studied relative extrema. What do we mean by relative extrema? We said we mean relative maximum and relative minimum. So when I say find the relative extrema of that function, what shall you find? You shall find relative maximum and relative minimum. We had a procedure for finding this one, and in general, when we were talking about those things, we were using the first derivative of the function to find all those things together. How was the procedure? We said if you have got a function f and it is required from you to find increasing intervals, decreasing intervals, critical numbers, and relative extrema, what shall we do? The first step that we shall do is to find the first derivative of the function. And then what were we doing? We were finding those numbers that were making the first derivative equal to 0 or f prime does not exist. Okay, does not exist. Or we can say that f prime does not exist or is undefined. Okay, so both of them is true. Either you're saying f prime does not exist or f prime is undefined. And then what were we doing? Of course, when we are finding those numbers, okay, those numbers that makes the first derivative equal to 0 or undefined or does not exist, we get numbers. For example, we get a number c, okay? We were putting that c on the real number line, okay? That's the real number line, and we were putting that c on the real number line. Then we were taking test numbers from here and there. Why? Because that c is making the real number line, dividing the real number line into two intervals. One interval that is less than c and one interval that's greater than c. So from each interval we are choosing a test number. Then we were putting that test numbers, okay, into the first derivative of the function. So we were putting a and b in the first derivative of the function. If that result was less than 0, as we said, we do not take care about the value. We are just considering the sign of that thing. Okay, the sign in here, what will we get, positive or negative? If it was less than 0, that means if we get a negative number, we say that the function is decreasing in that interval. Okay, and if we put the test number in the first derivative of the function and we get something positive, that means greater than 0. Okay, from here we say that the function is increasing. So when we were talking about these things, of course, that c that we are finding is what is a critical number. Critical number. We are putting that critical number on the real number line and subdividing the real number line into intervals. Then we were looking at that c in here. That c would become a relative extrema, or it may not become a relative extrema. How do we know that that critical number is a relative maximum or minimum? We are checking this side and that side of the number c. If this side is decreasing, for example, if you put it here, okay, if this side is decreasing and that side is increasing, so that number is what? Is relative minimum. If you've got c like that, if it here is increasing and here is decreasing, okay, that one is increase, that one is decrease, that one is decrease, and that one is increase. What do we get? That means on that side it's increasing and then it is falling. So that number is what? Is relative maximum. How about if you have got that this situation? Both of the sides are decreasing. We cannot say that this one is a relative minimum nor a relative maximum. Again, if you have got C here, if both of the sides are increasing, both of the sides of C are increasing, again, we cannot say that this one is a relative extrema. So in general, the procedure that we did in here for 3.1, okay, decreasing and increasing relative extrema and critical numbers, we are in general working on the first derivative of the function, okay? That was a general review of section 1 in chapter 3. Now I'm coming to concavity and points of inflection. What is concavity and what is an inflection point? In the lecture notes, both of them are defined in separate places, in separate boxes, but I will explain it first all together, and then I will give examples on both of them. So let's first talk about concavity. What is concavity? Generally speaking, we say that a function f is concaved up if f prime is increasing, okay? And we say that f is concaved down if f prime, I mean the first derivative, is decreasing. What does that mean when I say f prime is increasing or f prime is decreasing? Of course, we said when we say f prime, that means the slope, okay? If we say the first derivative or slope, this gives the same meaning. That means slope is increasing, and here we say that slope is decreasing. So in general, we have got, for example, this one is concave up, and that one is concave down. This one is a cup faced up, and that one is a cup faced down. Here the slope is increasing. Why? Because whenever we are drawing a tangent line, okay, if you look at this one, the slope is starting to increase, coming from here, decreasing, then it starts to increase. But here if we are searching for the tangent lines, I mean, if you're looking at the tangent lines, we see that the slope is falling, okay? It's coming from here, increasing, and then it starts to decrease, to fall. So since the slope is decreasing, it is falling, then we say that this one is concaved down, okay? Or the first derivative is decreasing, so it is concaved down, and that one is concaved up. Let's come to the definition of inflection point. Inflection point. What is an inflection point? An inflection point is the point, okay, is the point where concavity changes. What does that mean when concavity changes? That means if I have got a number here, okay, I've got a number here. Here, if I have got concave up, and here I have got concave down. Since I look at C, on the left side it is concaved up, and on the right side it is concaved down. Since concavity changes from up to down, so I say this one is an inflection point. Again, I have got another situation. Oh, here is one, and here I have got another case, not situation. Here, for example, I get here, that one is concave down, and here is concaved up. Since from the left it is down and it is changing to up from the right, since concavity changes from the, at that point, so we say that this one is also an inflection point. I've got two other cases. I've got C, for example, again here. Here I have got concave down, okay? And here I have got concave down again. Look at this, left and right, they're both concave down. Since the concavity doesn't change, it is still concave down, so we say that that one is not an inflection point. The same thing here. If I have got concaved up and concaved up, since the left side is concaved up and the right side is concaved up, so the concavity doesn't change, it's just up. So I say that that C is not an inflection point. Okay. In general, when we are talking about concavity and inflection point, we are using the second derivative to do the procedure, okay? To find the concavity of a function and inflection points of a function, we are using the second derivative of the function. So let's do the first example, or let me tell you the procedure of finding the concavity of a function and its inflection points. So what is the procedure? First, we have to find the second derivative of the function. Okay, a function is given to you, it says find the concavity of the function. So what shall we do the first step? We have to find the second derivative of the function. Second, we are finding those numbers in the domain of the function that makes the second derivative equal to 0 or second derivative undefined. Okay, undefined or does not exist gives the same meaning. Then, when we are finding those numbers that makes the second derivative equal to 0 or undefined, I'll get, of course, a number because I'm finding it, okay? Let's consider that number is C, okay? The third step, what am I gonna do? I'm gonna put that C on the real number line, again, like we did previously for increasing and decreasing functions, okay? I'm putting that number C that I found for these two things on the real number line. So what does that C do? It is dividing the real number line into two subintervals, or if I have got more numbers, I will have more subintervals, okay? So then what shall I do? I have to take a test number from each interval. That is an interval, and this one is also an interval. So I'm taking A from here, B from there. Any number, just a test number from there, okay? And then what do I have to do? Look what we did. We found the second derivative, finding those numbers that makes the second derivative equal to 0 or undefined. I'm putting those numbers on the real number line. Then I'm finding A and B. Okay, I mean test numbers. I'm choosing test numbers. The first step is what? I'm putting those test numbers in the second derivative of the function. Okay, I'm putting those test numbers in the second derivative, not the first derivative, because when we are talking about concavity and inflection points, we are using the second derivative of the function. Okay, when I'm putting that numbers into the second derivative of the function, I will get either that numbers are less than 0 or greater than 0. Okay, if it is less than 0, that means the number that I get here is negative. I care about sign again, positive or negative. I don't care about the value, whatever I get. So if it is a negative number, then we say that the function here is concaved down. Okay, for example, I put that A in the second derivative and I get a negative number. Since it is negative, so I will have here negative numbers and it is concave down. That means the cup that I have got is facing down. Okay, that is down, concaved down. If I get that, if I put B in the second derivative of the function and I get something that is positive, okay, then I say that the function that I have got is concaved up here. Okay, so I get positive numbers here and here is concaved up. Okay, that's the procedure of finding concavity of a function using the second derivative of the function. So And then how do you find an inflection point? As we said, that number will be an inflection point or will not be an inflection point. How do I know that that number is an inflection point? If the concavity changes, that means if it is changing from up to down, from down to up, I can call this one an inflection point. If it didn't change, if the concavity didn't change, so I will not call it as an inflection point. Okay. Now we have got an example, page 3. I have got example 3.2.1. Of course, it's in chapter 3, section 2, first page. It says determine, let me write the question for you. Determine intervals of concavity for the given function. And of course, it doesn't require the inflection points, but I will also add this part and find its inflection points if exists. What is the function that is given to us? F of x, that's equal to 2x to the power of 6 minus 5x to the power of 4 plus 7x minus 3. That's the function which is given to us, okay? As I told you, in the question, in the example that we have got in the course material, it says only find the intervals of concavity of the function. And I've also added what? Find its inflection points if it exists, okay? So what shall we do? Solution. We shall find, as it is written in the procedure, we shall first find the second derivative of the function, okay? So we have, for finding the second derivative, of course, I have to first find the first derivative of the function, and then I can find the second derivative. Okay, how is this one? How can I find the first derivative of this one? 2x to the power of 6. Of course, the 6 comes down, becomes 12x to the power of 5. This one, as you know, this one is decreased by 1, minus that 4 comes down, multiplied to 5, that will equal to 20x to the power of 3 plus 7. Okay, the derivative of this one is only 7, and that one is what? Minus 3. The derivative of a constant number is 0. So that's the first derivative of the function. But what do we need here? Here we need the second derivative of the function. So I have to find the second derivative of the function, f double prime of x. That's equal to what? 5 multiplied to 12. That's equal to 60x to the power of 4. Minus, because that 5 multiplied to 12 is equal to 60. X to the power of 4 decreased by 1. Okay, the power. And then 3 multiplied to 20 is equal to 60x, and the power is decreased by 1, so that's 60x squared. And of course, the derivative of 7 is equal to 0. Now, what shall we do? Look, the first step is finding the second derivative. The second step is to find those numbers that makes the second derivative equal to 0 or undefined. Do I have anything that makes that function undefined? No, I do not have anything. So I'll find those numbers that makes the second derivative equal to 0. Okay, that was the first step. I'm doing the second step. So I'm putting f double prime of x equal to 0. What does that mean? F double prime of x equal to 0. That means that terms are equal to 0. So 60x to the power of 4 minus 60x squared is equal to 0. That's an equation, and you know how to find, that is an equation, and you know how to solve an equation. Here we have got 60 as a common factor. Okay, 60, I'm taking it out from here and there. And then what do I have? I have got x to the power of 4 and x squared. What is common between those two terms? Of course, x squared is common between those two terms. So I will take out x squared also. What remains here? x squared is remained here, minus here 1 is remained because I have taken out 60 and x squared together. That's equal to 0, of course. Okay, now what do I have? Of course, I'm solving this one, 60x squared. This one, I'm opening the bracket, expanding it. You know that x squared minus 1 is changed to x minus 1, x plus 1, that's equal to 0. So x squared is equal to 0, or x minus 1 is equal to 0. As you know, I have got this one multiplied to this equal to 0. So either this one is equal to 0, or that one is equal to 0, or x plus 1 is equal to 0. Okay? So what do I get from this? I get x is equal to 0, x is equal to 1, or x is equal to minus 1. You know how to do that. You're simply taking this one to the other side. That's a linear equation. Okay, now what do I have to do? I have got those numbers, but be careful here. Those numbers are not critical numbers. We are working on the second derivative of the function. When we are talking about the second derivative of the function, I do not have critical numbers. I have got inflection points, but I cannot straightforward say that those numbers are inflection points. I have to check it out, okay? I've got this number, that number, and this number. Okay, what shall we do? I'm simply putting those numbers that we have found on the real number line. Okay. Of course, I'm putting them minus 1 here, 0 here, and 1 here. Okay, that's the real number line. When I'm putting those three numbers on the real number line, how many intervals do I have? I have got an interval from minus infinity to minus 1, an interval that's between minus 1 and 0, and another interval that's between 0 and 1, another interval that's between 1 and infinity. Since those numbers have divided the real number line into sub-intervals, so from each interval I'm choosing a test number. A number that's less than minus 1, I can choose minus 2. You're free to choose minus 3, minus 4, minus 5, doesn't make a difference, but we are choosing the simplest number, that's minus 2. A test number that is between minus 1 and 0, I can choose minus half, okay, as a test number. And a number that is between 0 and 1, I can easily choose half, okay, or whatever number you want. And a number that's greater than 1, you can choose 2 as a test number. 3, 4 doesn't make a difference, okay? Then, what did we say? Here, we did the procedures. We found f double prime. We found those numbers that makes the second derivative equal to 0. We put the numbers on the real number line. We chose test numbers. And then where shall we put the test numbers? We have to put them in the second derivative of the function, okay? So, what shall we do? I'm putting those test numbers, okay? F double prime of minus 2, f double prime of minus half, okay? F double prime of half, and f double prime of 2. Okay, we put those test numbers into the second derivative of the function. Why? To check whether it is positive or negative. Why? To check whether they are concave up or down. Okay, let's put this one, those test numbers into here. If you look at that function in here, if I put minus 2 into here, that bit is always positive. Why? That bit is always positive. Why is it always positive? Because I have got x squared here. Whatever number I'm inputting here, negative, 0, positive numbers, since it is x squared, I will always get a positive number. So that will be a positive number, okay? I'm putting minus 2 into here, I will get a positive number. Then I'm putting minus 2 in here. Minus 2 minus 1 is a negative number. Then I'm putting minus 2 in here. Minus 2 plus 1, it is also a negative number. I don't care about the value. Again, I just care about the sign of the function. Okay? So I have got positive, multiplied to negative, multiplied to negative, negative, negative is positive, positive multiplied to this one is positive. So in that interval, when I put negative 2 in the second derivative of the function, what did I get? I got positive numbers. Since it's a positive number, so here in that interval, whatever I have got is positive. What does positive mean? As we said, if it is positive, that means the function is concaved up. So here the function is concaved up. Next, we are putting minus